Hello, and welcome to our second video covering topics in section 7.1. In this video, we will be discussing dynamical systems. Okay, so we're going to start with an example. So in this kind of, silly example, we are saying a stretch of desert in northwestern Mexico is populated mainly by two species of animals, coyotes and roadrunners, and we wish to model the populations, C of t and R of t, of coyotes and roadrunners respectively, t years from now if the current population is C0 and R0. Okay, so this is our setup, coyotes and roadrunners, and suppose we have this recursive population model. So we're saying, all right, if we know C of t, the number of coyotes at a certain time, and R of t, the number of roadrunners at a certain time, then this population model says that the number of coyotes a year from this time is given by this equation. And similarly, we can say that the population of roadrunners, well, if we know them if we know number of coyotes and number of roadrunners at a certain time, then we can say that with certainty what the number of roadrunners will be a year from that time with this equation. And I encourage you to think a little bit about what these coefficients, like what their physical meaning might be. But let's just take this as a given. This is our population model. So, okay, we're in linear algebra. Let's matricize this bad boy. Doing that, all right, so we have our matrix now of coefficients, and we have this vector CT, RT, and then matrix multiplication of this vector C of T, R of T will get us the population 1 year later. So moving forward in time ends up being equivalent to multiplying by this matrix. Just for a piece of cultural knowledge, x of t, we'll call this ct, r of t. This is called the state vector often in dynamical systems. And then, okay, we've got our matrix A here. And so suppose now we know the current population. So t equals 0 is now. Often this is just a written x sub 0. So we know this population right now. C sub 0, R sub 0. And we want to know the population t years in the future. Well, okay, starting now, applying matrix A will get us 1 year in the future. But now this will be our new state vector. And so we have to apply A to that to get 1 more year to the future. Now this is our new state vector. Apply A again to get 3 years into the future, and so on. And if you apply A t times, you will have gone t years into the future. And so we have this, what looks like a closed form for our population, which is that, the population at time t is A, matrix A raised to the t times the population at time 0. Okay, and given this, all right, we can say, all right, well, suppose we know the population, we've got 100 coyotes and 100 roadrunners right now. Then we could say calculate how many coyotes and roadrunners there will be 10 years in the future by taking a to the power of 10 and then multiplying our state vector by that. And if you plug this into Desmos matrix like I did, you will see that it's about 80. We end up with about 80 coyotes and 170 roadrunners. So, okay. Now, we saw in the last video how eigenvectors and diagonalization can help with calculating powers of a matrix efficiently. We're also going to see how eigenvectors and diagonalization can help with finding closed formulas for C of t and R of t here. You might be thinking, wait, I've got a closed formula here. X of t is just a to the t x0. And so if A is diagonal, then yes, you do have a straightforward closed formula for the number of coyotes and the number of roadrunners, because, okay, A of t is just lambda 1 to the t, lambda 2 to the t, and then zeros on the off diagonals. And then this formula here, x of t equals a to the t x0, well, this just implies, okay, the number of coyotes at times t is lambda 1 to the t times the initial population, and the number of roadrunners at time t is lambda 2 to the t times the initial initial population of roadrunners. Wait, did I say roadrunners both? Okay, anyway, you get the idea. But what if A is not diagonal, which it's not in this case? Then, when you take A to the t, do you have a formula for the entries in terms of just the entries and time? You could try to take a few iterations and see if you can find a pattern, but just in general, good luck finding a closed formula for these without something systematic going on. And so this is where eigenvalues or eigenvectors and diagonalization will help, because if we can diagonalize our matrix, then we can, in fact, find easily closed formulas for the population of coyotes in the future and roadrunners in the future. So let's see how that works. Okay, here's our setup, our state vector, our matrix, and then we have this equation. State vector at time t is a to the t times our initial vector, our initial population. Now, all right, don't ask me how, but I've got an eigenbasis. No, you don't want to know. I know a guy. You can get me an eigenbasis if I need to. But yeah, so here it is. We've got V1 is our first eigenvector is 100, 300. So this is 100 coyotes and 300 roadrunners. And our second eigenvector is 200, 100. So 200 coyotes, 100 roadrunners. And these the associated eigenvalues are associated with V1 has eigenvalue 1.1 and V2 has eigenvalue 0.9. Okay, so what this means is that A applied to V1 will be 1.1 times V1, and A applied to V2 will be 0.9 times V2. And now let's ask what happens in our population model if our initial state, our x0, is actually V1. So our initial state is 100, 300. Well, okay, then AT times our initial state, which is going to be V1, is just going to be 1.1 to the t times V1. And in this case, okay, so this is our initial vector, then this equation up here, C of t R of t equals a to the t times our initial vector. This implies that C of t is 100 times 1.1 to t, and R of t is 300 times 1.1 to the t. So again, we have closed formulas for our coyote and roadrunner population if we start with an eigenvector. And as we can see in this situation, this seems to be a happy balance of or ratio of coyotes to roadrunners, because in this scenario, each population grows by 10% every year. So, okay, what if we started with the other state, with the other eigenvector? Is this being our initial vector? Well, okay, a to the t times our second eigenvector. Well, every time we apply a, it actually multiplies our vector by 0.9. So a to the t times our eigenvector is 0.9 to the t times our eigenvector. And then again, looking at this equation and knowing that x of t is c of t and r of t, this implies that we get the closed forms the number of coyotes is 200 times 0.9 to the t, and the number of roadrunners at time t is 100 times 0.9 to the t. And in this case, both populations are decreasing by 10% each year. So this seems to be not a happy ratio for the populations. Okay, so we know what's happening if we start on an eigenvector, we get these closed formulas. But what if we have just some generic starting state? This is what we're after. We're after a closed formula for the state vector at time t, given some arbitrary initial condition. Well, our first job is to calculate the coordinates of our initial vector in the basis of eigenvectors, so in the eigenbasis. So we're trying to find some C1, C2 such that, our initial state x0 is C1 times the first eigenvector plus C2 times the second eigenvector. And we've seen ways to do that at this point. But if we do that, then okay, our state vector, like going back up to this equation, is going to be a to the t times our initial vector. And then by linearity, we pull out the coordinates, and we have a to the t times the eigenvectors. And we get, as a final formula for our state vector, C1 is 1.1 to the t times our first eigenvector plus C2 times 0.9 to the t times our second. And so here we go. We have the closed formulas. The number of coyotes, the number of coyotes is the coordinate of our initial state in the eigenbasis, the coordinate of the first eigenvector in the eigenbasis, times 100 times 1.1 to the t plus c2 times 200 times 0.09 to the t. And our roadrunners, okay, there's similar formulas there. So, okay, how do we visualize a dynamical system? Now that we have this closed formula, we've used an eigenbasis, we found a closed formula for a system, but how do we visualize dynamical systems? Okay, so here's our formula once again, and let's just plug in a specific initial condition. So let's just say we have the same number of coyotes and roadrunners, 1,000 each. Well, okay, first thing we got to do is find our C1 and C2. And if you can check that the coordinates are 2 and 4, like 2 times 100 plus 4 times 200 is 200 plus 800 is 1,000, and then 2 times 300 is 600, plus 4 times 100 is 400, so 600 plus 400 is 1,000. So indeed, these are the coordinates. And so our state vector is this. And so what we do when trying to visualize a dynamical system is we think of the state vector as a vector, and we think geometrically what's happening to this vector as t changes. And so your book gives us this nice diagram. There's a lot going on, so let's see what's happening. So first, your book has a line for the span of this first eigenvector v1, and it makes a line for the span of the second eigenvector v2. And then what it does is it's saying, okay, well, the initial state vector x0, this is 2 times v1 plus 4 times v2, so you end up here. And then the next state vector, so marching forward in time 1, you get, well, what's happening here with these when you march forward in time? Well, when you march forward in time, the component of your state vector that's in the v1 direction, that increases by 10% each time you march forward in time. It's increasing by 10%. Whereas the component of your state vector that's in the v2 direction, that actually is decreasing by 10% each time. And so you march forward in time, 1 year, you get to here, 2 years, you get to here, 3 years, you get to here. And it's hard to tell what's going on in just 3 years. It looks like it even could be linear or something. But actually, if you march forward in time, if you jump 10 years up, 10 years forward, you get all the way up here. And so to see kind of what's happening generally, it's nice to plot out a bunch of points and connect them with a line. And you can kind of get a general picture of what's happening. And okay, we started here, and if your model works and it makes sense to go back into the past, you can say, all right, well, I know what this state is and at time 0, and if my model is right and works in the past, then I can just say, all right, well, 5 years ago, it must have been whatever I'd get when I plugged in t equals 5, minus 5. So, okay, we've got this kind of trajectory of the population here. But let's think about other starting conditions, because that was just one that we looked at. And so often when visualizing dynamical systems, it's like, okay, you've got your eigenvectors, the span of your eigenvectors, and usually want to test a trajectory kind of in each region that these spans kind of demarcate. So you want to test a trajectory with an initial condition below the span, one between the spans, and then one above the span. And doing that gives you an idea kind of in general of what happens to your populations. Whoops. So yeah, the idea is, all right, if you picked a vector on the span, then, all right, as we saw, both populations, say if you start on the span of V2, both populations are decreasing and they just steadily decrease down to 0. If you pick a initial condition on the span of L1, then both populations increase 10% each year, and that continues on indefinitely. And so this is a good ratio. Let's see. Yeah, 1-3 ratio of coyotes to roadrunners seems like good for their populations. A population of twice as many coyotes as roadrunners seems very bad. And then, okay, yeah, test what happens at other trajectories or other initial points in between. Kind of makes sense here that if you have even more coyotes than roadrunners than just 2-1, then you're just going to go to 0. Both populations are just going to decline even faster. Like the coyotes are just going to eat all the roadrunners, and then the coyotes are going to starve. And if you start a little bit, say you have a slightly more favorable ratio than 2-1, like I guess slightly less than 2-1, then okay, the number of coyotes and roadrunners does decrease. They each decrease, but their ratio gets more and more favorable until at some point both of the populations start increasing and start approaching, the span of this eigenvector. And then, okay, if you chose even more, or if you have even more roadrunners, then okay, you've got plenty of roadrunners. Coyotes have plenty of food. Both populations are going to be increasing because you've got way more roadrunners than the coyotes can handle. And okay, the coyotes, they'll eat a lot and they'll bring that population down, but they're both gonna continue increasing, and it looks like they're gonna again approach the span of this eigenvector. So that's the idea for visualizing a dynamical system. You've got your span of your eigenvectors, and then you test trajectories in all of the regions. And mathematically, we can actually make sense of these spans and these trajectories in all 4 quadrants, even though physically only, a positive population of coyotes and roadrunners makes sense. But okay, mathematically, these equations can hold with, you can put negative initial conditions here, and this, mathematically makes sense. And the reason you might do this is so that you can get a better sense of what kinds of graphs you have. So when you look at this, you can say, oh yeah, these are hyperbolas. All right, nice. Just so you know, this bad boy here is called a phase portrait. And it's basically the visualization of a dynamical system in 2 dimensions. So okay, to summarize, suppose we have a discrete dynamical system. Wait, what's a discrete dynamical system? Well, it's one where your state vector is marching forward by a discrete amount of time. So in this case, like each year. And so, okay, so you've got a dynamical system set up recursively like this, where you have an initial state vector. Then your state vector can be written in what looks like a closed form like this. X of t is a to the t x0. But as we saw, finding a closed form for a to the t, what we need to do is, we need to find an eigenbasis for a. And then, okay, so this is our eigenbasis. AV1 is lambda 1b1 all the way up to AVN is lambda nbn. And then you find the coordinates of your initial state vector in this eigenbasis. So your initial state vector is C1 V1 plus all the way up to Cn Vn. Then an actual closed form for your state vector, x of t, is this, which you get by linearity, looks like this. And then because these are eigenvectors, your closed form is your state vector is c1 lambda 1 to the t v1 plus all the way to cn lambda n to the t vn. Okay, so this has hopefully been a motivating problem, like a real life problem. Well, okay, this is based off of a cartoon, so hard to say it's real life. But I do believe that actual population models do, follow. Sometimes they do have these, kind of simple trajectories and relationships, and so real life scenarios can be modeled very similarly to this. And yeah, I think dynamical systems are cool. So even though it's optional for our text, it's not optional for our class. All right, see you in the next video where we really hammer on how to get eigenbases. See you then.